In this video, we're going to continue with factors that affect equilibria and that cause them to shift in one direction or another, and then see how Le Chatelier's principle is going to act to overcome that shift. So we can look at another factor called the temperature changes. So you might increase or decrease the temperature of an equilibrium system, and that will lead to different shifts. So we're going to continue with the same reaction that we had earlier. Our reaction was X gas plus Y gas equilibrium Z gas plus heat. So we're dealing with an exothermic system here. Endothermic behaves a little bit differently, and we'll see that as well. So essentially, suppose we disturb our system. Suppose that we increase the temperature of our system. What we're doing when we increase the temperature is we are adding heat. In other words, we're adding heat. So that's what increasing the temperature means. So what do we want to do? We've upset the system. We've added more heat than there should be there. So we want to get rid of some heat. So we want to remove heat to lower the temperature. If we've added heat, how do we we need to undo it by removing heat. So what direction do we need to go? Well, here we have an exothermic reaction, right? We've added heat to this side here. There's too much heat now. So to get rid of the heat, we need to go to the left side. The heat is going to decompose the Z, and we're using up the heat. So we're going towards the left side. So if we added heat to an exothermic reaction, the reaction will go from right to left. So we are going, so this is the left side. The reaction is going to proceed to the right side in order to get rid or use up the heat that was added there. And that's for an exothermic reaction specifically. So how the system is affected depends on what type of reaction you have. So here, when we increase the temperature for an exothermic reaction, we had to shift towards the left side to reduce the heat that was added. However, suppose we reduce the temperature, we remove heat. Now we want to produce more heat, so the reaction will go the other way. So essentially, temperature changes. How does it affect an equilibrium? Well, it depends on if the reaction is endothermic or exothermic. So if you're, let's say, endothermic, let's do an example here. If you're endothermic, suppose I had N2O4 gas plus some energy, so heat, and that produces 2NO2 gas. Well, let's just do an experiment here, figure this out. So suppose that in this scenario, I increased the temperature. Well, what that would do is it would cause my reaction to shift. Maybe you can predict it. I've increased temperature. It would cause my endothermic reaction to shift from left to right to get rid of the heat on the endothermic side. So here we have an endothermic example. When I increase temperature, shift from left to right to reduce the heat that was added. But let's say that instead I decreased temperature, I removed heat. Now to make more heat back on that left side, I need to shift from right to left instead. And that's for an endothermic system, okay? But if it was for an exothermic system, so suppose we had H2 gas plus I2 gas, and that produces 2HI gas plus heat. This is exothermic because of the heat term on the right side, on the product side. So as we saw, if I increase temperature, well, the reaction is going to shift from right to left to get rid of the heat that was added. But if I decrease temperature, the reaction is going to shift from left to right to add more heat that was removed. So think of the heat or energy there almost like a product or a reactant that you're adding or removing, and you want to essentially counterbalance what you've done. You want to undo essentially what you did. You want to, if you added heat, you want to remove it. If you removed heat, you want to add it back. And so that's why the shifting will depend on whether you have an endothermic or an exothermic reaction. Now, the other important point to understand as well is in the previous video, we saw that when you change concentrations, your K is constant even when your new equilibrium is established. When you change temperature, your K changes. So changing temperature changes K. Changing temperature changes K. And that's because when you're dealing with reactions like this, the rates of the different sides are affected differently by the temperature. Because if you go, this way, it's exothermic, but if you go this way, it's endothermic. So the temperature affects endothermic and exothermic rates differently, which is why you'll establish a new K altogether. So in the case of changing the concentration, the K remained the same. But when you change a temperature, the K will change at the end. You'll still establish a new equilibrium, but at that new equilibrium, your K is going to be different than what it was from the original equilibrium, because your endo and exo rates are affected differently based on the change in temperature. So that's important to understand. Concentration changes didn't affect K, but temperature changes do. And that's why we report the K value with the temperature generally. But let's go take a look at what this looks like graphically. So if we're making a graph to go over a scenario for the X, Y, and Z increasing temperature. So let's go ahead and put that, we're at equilibrium right now, concentrations aren't changing. Then we come and we make things a little bit unhappy. We increase the temperature. So when we increase the temperature, remember that we want to reduce the heat that was added there by using up the heat, essentially going from right to left. So heat in Z will be used up, and then more X and Y will be produced. So we're going to see that slowly over time, Z will decrease and then stabilize. And that's because it's reacting with the heat to make more Y and X. So that means that slowly over time, Y will increase and then stabilize. And then X will increase and stabilize. And I didn't quite stabilize them all at the same spot. They should essentially stabilize so that you reach equilibrium. So the point where they all stabilize and reach the new equilibrium, it's left the flat line there. Let's do that a bit closer to here. I'm a little bit off, but essentially where they've all flatlined completely and are no longer changing. So this is the old equilibrium, and this is a new equilibrium. And there is a new K now because the temperature affected the rate of forward and reverse differently, since one is exo and one is endo. So unlike concentration changes, again, the K value changes when you change the temperature. Okay, so that's super important to remember. So in this video, we saw how temperature affects shifts in equilibrium systems. We saw it depends on whether you have an endothermic or exothermic reaction. We also saw that the K value will actually change when you change the temperature, unlike changing the concentration of reactants that you add or remove. So one last thing to think about before you go to the next video is, how will the K value change? So for an exothermic reaction, if I've increased temperature, will K go up or down? Think about that. Or for an exothermic reaction, if I decrease temperature, will K go up or down? Write out a reaction, try it out, try to figure out what you think will happen, those K values, and I encourage you to research it after to see if you were on the right track or not.